Okay.
Keith is going to talk about the biggest known prime number.
The arrows as usual.
Yep.
Okay. All right. So we all know that there are infinitely many prime numbers, and so the list never ends. But since we don't have simple formulas that will generate infinitely many primes exclusively, there was always a largest known prime number. So you see in the newspapers every couple of years a little article, oh, they found a new prime bigger than all the ones that had been known before. So the latest instance of this was this year in January. So I don't know if this is working? Well, in any case, so there we have the prime in the middle there, 2 to the around 77 million, and so on. It's a 23 million digit number, and so this is the new record biggest known prime. Inevitably, it will be surpassed at some point. I hope that didn't happen this morning. In any case, and as I indicated there, once they found it, once they had reason to believe it was prime, then they actually ran several different independent checks that had passed various primality tests to verify that it was indeed a prime. And so these types of numbers, 2 to the n minus 1 that are prime, these are called Mersenne primes. They don't have any practical applications. People interested in computational number theory just like to use them kind of as a challenge to keep finding bigger and bigger examples of prime numbers. It's way too big to be of any use in cryptography. If you use this number in cryptography, it will be noticeable right away. Its scale is far larger than the ones that are actually used. So I looked around at some articles after this prime was announced in the media to see what they said about it, and as usual, they got some facts wrong. So first of all, the first claim was that in order to verify primality, you have to divide it by every number that could possibly be a factor. Okay, so this is actually not true. The way you can test, I'll mention towards the end of the lecture, the way you test 2 to the n minus 1 to be prime, you do not actually do division by numbers that might possibly be factors to show that this is a prime. It's a different test that's used. The second claim there is that we think that 2 to the n minus 1 has a high probability of being prime when n is prime, but this isn't true because we only know 50 of these Mersenne primes, but there are way, way, way more Mersenne prime n below that 77 million exponent for which 2 to the n minus 1 is not prime. So in fact, it's quite rare that these 2 to the n minus 1 numbers are prime just because n is prime. And finally, this last claim was that encryption uses large primes because they're so difficult to find. Well, if they were difficult to find, we wouldn't be using primes so often in cryptography. Every time we go on the internet, these cryptosystems are based on generating very large prime numbers with hundreds of digits. And in fact, they're probable primes. Probabilistic primality algorithms are used, and if the number is not revealed to be composite after like 20 or 30 iterations of these probabilistic algorithms, you kind of declare it's an industrial-grade prime number, and you use it, but there's no airtight proof, but this has never led to any practical consequences that are negative for the use of such algorithms. So nobody's actually using prime numbers because they're hard to find in any sense. So the biggest prime numbers at present, the top 5 are listed there from most recent on down, and so they're all Mersenne primes. It's not always the case. I mentioned down at the bottom of the slide, for a brief period in the 1950s and around 1990, there were largest known primes that were not of this special form, but generally speaking, the largest prime has always been of this special form because there's a test for primality for these numbers that doesn't work on other numbers, and so it's much more efficient to use. And there was Numberphile with a video. Once they found the second most recent example in 2015, they printed it out on 700 plus pages, a very small type. And when the new prime was announced, overlaid on the video that I took a screenshot of here, there was some message that they were going to come up with a new video soon for the new Mersenne prime, and the video never materialized. It kind of waited for like weeks, like what's happening? I just kind of gave up. So in any case, so the story of these Mersenne primes goes back to Marin Mersenne. He was in France in the 1600s, and he was kind of a clearinghouse for all the scientific knowledge in those times in Europe people would write to him, he would write to other people. He was kind of a correspondent to a lot of the leading scientists, the Wikipedia of his day. During his correspondence, he at some point claimed that 2 to the n minus 1 was prime for these 11 exponents n that I've listed there. And, well, the small cases are very simple to do by hand, but once you even get up to 2 to the 19 minus 1, well, I guess you could do that. 2 to the 19 minus 1 was manageable. But 2 to the 31 is quite a big jump from 19, and that was just far too large for anybody to do by hand to verify the primality of 2 to the 31 minus 1. So his claim that these higher exponents led to Mersenne primes, or led to prime numbers, we don't know how he reached that conclusion, and it turns out, in fact, some of his claims with the higher exponents leading to primes was wrong, and he also missed a couple as well. So we'll see how this story turned out. It took over 200 years for kind of this primality status of 2 to the n minus 1 for n up to 257 to be completely settled. So why were people interested in these types of prime numbers back then? Okay, so we didn't have all the mathematical techniques or areas of math today back in those times, so it was a much simpler time mathematically speaking and otherwise. And so in particular, at that time, people were actually still interested in perfect numbers. Okay, so the perfect numbers are the ones whose proper factors add up to the number. The first two examples are 6 and 28. And there's a close connection between perfect numbers and Mersenne primes. Namely, Euclid showed that if 2 to the n minus 1 is a prime number, that 2 to the n minus 1 times 2 to the n minus 1 is perfect. And then about 2,000 years later, Euler showed that the converse is true as well for the even perfect numbers. Every even perfect number must arise in Euclid's form. So the number of Mersenne primes and the number of perfect numbers that are even, these are essentially two ways of talking about the same thing. So now we know there are 50 even perfect numbers, and the world is better for that in some way, I suppose. And after Euler proved this theorem, and it's really quite short, it was, about a little bit in his paper, he then wrote this phrase in Latin, which, if you look closely, you can see is in the middle of it is number perfect. In pares, what is that? That's odd, right? Not parable, odd. Something about odd perfect numbers there. A difficult question at the end there, right? So in English, he just kind of poses the question that, of course, odd perfect numbers are kind of mysterious, whether there are any or not, or proving there aren't any, or finding any examples. And just based on number crunching, there are no odd perfect numbers with less than 1,500 digits. So the consensus is they probably don't exist, but this is probably one of the oldest unsolved problems. If we would attribute to the Greeks who contemplated perfect numbers the question of whether there were any odd examples, maybe we could call this the oldest unsolved problem in math that we know about, but it's not clear that the Greeks themselves ever even thought about whether they are or are not odd perfect numbers. In any case, so that was one of the topics of study back then, perfect numbers. Nowadays, part of recreational number theory. If tomorrow somebody were to discover, this, perfect numbers are connected to, some structure attached to a p-adic field, and they're like, so maybe there's something we can do if we kind of absorb it into the mainstream. But for now, it's kind of an isolated little question. But it historically was important in raising interest in deciding when 2 to the n minus 1 is a prime. So it's pretty easy to see that for 2 to the n minus 1 to be prime, n has to be prime, because if n factors, the exponent factors, it's pretty easy algebraically to factor 2 to the n minus 1, but the converse is false. If n is a prime, the number 2 to the n minus 1 doesn't have to be prime, and the first two counterexamples are 2 to the 11 minus 1 and 2 to the 23 minus 1. I give the factorizations into primes for those, and interesting tidbit is that the factorization of 2 to the 11 minus 1 is kind of related to an important example in coding theory. There's some code over F2 in 23-dimensional space over F2, and it's called a perfect Golay code, and the perfectness of this code is related to the fact that 23 goes exactly into 2 to the 11 minus 1. In any event, the fact that these numbers 2 to the prime minus 1 often are not prime, you can already see if you check up to 100, only 10 of the 25 primes below 100 lead to a Mersenne prime. And as you stretch out the data, the rarity of these Mersenne primes for prime exponents becomes quite clear. So how did Mersenne's claim turn out? Well, I highlighted in red the exponents that he claimed would lead to a prime that, in fact, do not lead to a prime. So we start with 31. Euler figured out 2 to the 31 minus 1 is a prime. We'll discuss later how he did that. The problem, again, was that if you just naively compute out the number, 10-digit number, and try to trial divide by all the primes up to the square root, it just looks like an unmanageable calculation. But Euler, using some ideas related to quadratic reciprocity, found a way to massively reduce the number of potential factors to fewer than 100 primes to check, and so he was able to show that that number was a prime. But then you have to fast forward a little bit over 100 years for the next step, which was when Lucas showed that at the same time, Mersenne was wrong with 67. 2 to the 67, take away 1, is actually composite, but as often happens, you can prove numbers are composite without factoring them. So he had no idea how 2 to the 67 minus 1 factored, but he could show, based on properties that primes have and composites have, that this number had to be composite. At the same time, he did show that Mersenne was correct for exponent 127, that was a prime. And then it turns out, first discovery later was that 2 to the 6, a number that was off Mersenne's list that was prime. He missed 3 examples, exponent 61, 89, and 107. And then finally here, the status of Mersenne's last example, he was wrong. It's actually composite, and Lamer showed that in the 1920s. This is all pre-computer. Electronic computers didn't become available for use in scientific or mathematical investigations until sometime in the 1940s. So in summary, then, Mersenne, he got 2 things right. 2 exponents above 19 were right, but then he screwed up in 2 cases, and then he completely missed 3 cases. And so it took a long time to handle this. Of course, once computers enter the picture, all of this hard computational handwork just becomes trivial with the computer. And so we'll talk about that shortly. But first, I want to address this 2 to the 67 minus 1. That was the example that Mersenne claimed was prime that was not, but he couldn't find a factorization. So it was first factored by Frank Nelson Cole, after whom the AMS Cole Prize in Algebra is named. And there's the factorization up there. You can see it decomposes into a product of 2 numbers that are themselves prime. And then Cole famously claimed, when he was being interviewed by E.T. Bell, how did you find the factorization? 3 years of Sundays. So E.T. Bell was actually a PhD student of Cole. So I think he had a vested interest in trying to make this sound like a very dramatic event, factoring this number, again, completely by hand. But if you look at the paper that Cole wrote on this, he really uses actual techniques in number theory, quadratic residues and various things, such that, of course, he has to do a lot of numerical calculations too, but at the end of the day, he does find a way to write this number as a difference of 2 squares, and so thus we get a factorization. So there's a story that Bell liked to propagate that Cole went up to the board at a meeting of the AMS, I think at the time it was still the New York Mathematical Society, and he computed the power of 2, take away 1, and then he wrote down those 2 long numbers and multiplied them out without saying anything, and saw that the 2 results were the same, and then he sat down and everybody clapped, and so he gave this lecture without saying anything. But I think this sounds completely absurd, because nobody's going to want to sit through a lecture. They didn't have phones to occupy themselves, right? They're going to sit like, 30 minutes, when is he going to finish? This is absurd. So I think the story is completely made up. In any case, and the paper that he wrote shows he really used some ideas. He would not just stand there and multiply out the numbers. So in any case, but he did find it completely by hand, found this amazing factorization. Now let's go on to the computer era. So here we have a picture of the first computer that was used. I think it was at UCLA, the Western Automatic Computer. And once it was put to work to find these Mersenne primes, it very quickly found many new ones. This is far beyond the scale of human hand calculation, Remember, the last one that was found was exponent 127 by hand, but then in the 1950s, the computer very rapidly found examples of Mersenne primes with the exponents going up into the thousands. And then we see here, what are the practical applications of Mersenne primes? There's a practical application to postage stamp design. Right? So at Urbana, when the computer there found the Mersenne prime with exponent beyond 10,000, at least for several years, their outgoing mail postage stamp had that message on it. So, rare application of Mersenne primes to the real world. Are there any questions? Nothing? Okay. So, what happens with trying to find Mersenne primes with computers? So nowadays, of course, this is all done by computer. So I mentioned before that Lamer had shown 2 to the 257 minus 1. That was Mersenne's last claimed prime actually was composite. But Lamer was unable to find a factorization. I don't know if Frank Cole was around. He probably gave up didn't want to spend 10 years of Sundays factoring that one. So you wait until the 1970s when a factorization was found, and then the next year, the full factorization was found by computer, and I tried on Wolfram Alpha. It took about 3.5 seconds to factor this number, or at least to find a non-trivial factorization and to know that the second number was at least composite, so there should be further work to do. In any event, so of course we've made a lot of progress since 1980 as far as the speed of computers is concerned. And so if you go online now to the great internet Mersenne prime search, this is kind of a collaborative computational search to find Mersenne primes, and you can, if your laptop is idle sometime, you can kind of sign up to join the search, and if your laptop detects a potential Mersenne prime that turns out to be prime, then you'll get your name in the newspaper, and I think there might still be a prize for, I think, the next some number of millions of digits. There might be some financial incentives too. But so for example, I think that the prime that was found this past January, it was found on some computer in some church in, I think, Missouri. Okay, there was a person who had a bunch of computers in their church, and they just kind of set them to run, and so I think they might have gotten some small financial compensation for that. In any case, I've listed here the number of examples of Mersenne primes that have been found in the various decades since computers took over from humans for the calculations. And you can see that we got 11 examples in the 1950s and 1960s, which is about how much people could do by hand before then. So it remains, of course, to be seen if any further Mersenne primes will be found in the 2010s. If they do get found, I will update the slide accordingly. All right. So let's talk now about why we should expect that there are infinitely many Mersenne primes. So we believe there are infinitely many, but where does this come from? So this touches on what Alvaro is doing in his course in terms of probabilistic heuristics. What theorems about primes suggest might be a way to model the primes to let us guess the answer to various statistical questions like, how many Mersenne primes should you expect up to 77 million or 80 million? How many should there be? Right? We found so far 50. So the key idea is to take the prime number theorem and to turn it into a heuristic probability statement. Namely, because the prime number theorem tells us the number of primes up to x grows like x over log x. It suggests the idea that goes back to Gauss that the density proportion of primes around a large number x should be roughly on the size of 1 over log x. And so that suggests the probability that m is prime should be considered as 1 over log m. Strictly speaking, this is a nonsense statement. On the one hand, when m is 2, it certainly makes no sense because log 2 is less than 1. So 1 over log 2 can't be a probability. But more to the point, primality is not a notion of probability. Number is prime or not. So this notion of calling the probability the number is prime by a formula is just to help generate ideas that we might hope to prove later by more rigorous methods. But it certainly helps to know what you're trying to prove rather than just kind of stumbling around in the dark. So in particular, if we accept this probability of a number being prime as some reasonable guess, then we can recover the prime number theorem. Heuristically, the number of primes by this probabilistic model, the expected number of primes up to x should just be the sum of the probabilities up to x. And if you sum 1 over log m from 2 up to x, it grows like the integral, and from 2 up to x, and that grows like x over log x. So if you accept the probabilistic model inspired by the prime number theorem, ideas from probability would then let you recover the prime number theorem. So with this probabilistic idea in mind, let's now address the question of how many Mersenne primes should you expect, how many 2 to the n minus 1 should be prime for n up to x? How should this function grow? Should it be like x over log x over log x squared, the square root of x, or what? Okay, so what we can do then is just sum the probabilities for this type of counting and see what's suggested. So let's do that. I want to think again, the probability number is prime is 1 over its logarithm, natural logarithm. So let's sub in for that numbers of the form 2 to the n take away 1. So the expected number of n up to x that should make 2 to the n minus 1 a prime, we'll just sum up 1 over log of 2 to the n minus 1 for n up to x and see how that behaves. How does that grow as x grows? Well, of course, for n large, that's basically 1 over log of 2 to the n. So drop the minus 1, bring out the exponent. Oh, so I can just take a log 2 outside. I'm summing 1 over n for n up to x. And the sum of the harmonic numbers grows like the integral, 1 over t up to x, and that's log x divided by log 2, so log base 2 of x. So this is the heuristic suggestion for our probabilistic model. The number of Mersenne primes, when the exponent goes up to x, should grow something like logarithmically, log base 2 of x, which is very slow, right? Right now we're up to 77 million, and we only have 50 examples. And so this model is kind of consistent with that, the very, very slow growth in the frequency of Mersenne primes. But the count does get big if you wait long enough. The logarithm diverges, but very slowly. And so this would suggest that there should be infinitely many Mersenne primes, but they should really become more and more rare, increasing in quantity like logarithmic growth. Now, I want to point out one way to see that this probabilistic model is absurd as a rigorous statement is you can plug in other expressions besides 2 to the n take away 1. If I plugged in 3 to the n take away 1 into this summation, it would lead to exactly the same estimate. So I could say, the number of primes of the form 3 to the n take away 1 should be roughly log base 2 of x. But this is absurd. Why is this absurd? They're always even, okay? So this notion of probabilistic model has to be taken with a grain of salt. Under reasonable circumstances, it would suggest the truth. So anyway, but it's still nice because it suggests what should happen, and this appears to be roughly what's happening. But the constant out front, just straight log 2, is not really accurate. The actual conjecture, you have to kind of futz things when you're doing this probabilistic modeling with some constant factors, kind of like a conditional probability involvement there. So Lenstra, Pomerantz, and Wagstaff, by thinking a little bit more carefully, suggest that the better asymptotic estimate for the number of Mersenne primes up to x should not be log 2 of x, but e to the gamma times log base 2 of x, where gamma is Euler's constant, and e to the gamma is around 1.78. So you have to almost double log base 2 of x to get a better conjecture, and if you try to plug in 80 million, remember we know the Mersenne primes now up to 77 million, there are 50 of them. If you plugged in 80 million into e to the gamma log base 2 of x, you get around 46.7, which is not a bad estimate given that the actual data is 50. And we really have too little, the amount of data is just too small to be convinced or not convinced that this probabilistic conjecture is accurate. You really should expect hundreds and thousands of primes before you might expect a reasonable picture to emerge. But in any case, log base 2 of x has at least an order of growth, seems to be a good explanation, and we have a more refined estimate for that. In any case, so this is why we expect that there should be infinitely many Mersenne primes. In the other direction, of course, you can say, what about Mersenne composites? Clearly, all but 50 of the ones up to exponent 77 million have turned out to be composite, so there should be a lot of those. So can we give a proof, at least, that there are infinitely many Mersenne composites when n is prime? For prime n, I would like to show 2 to the n minus 1 is usually composite. So Euler sort of did that, not completely. So there's still not a proof that 2 to the n minus 1 when n is prime is composite infinitely often, but here's kind of a conditional proof. If p is a prime for which 2p plus 1 is also prime, and p is 4m plus 3, then Euler showed that 2 to the p take away 1 is, in fact, composite if p is bigger than 3, because it's divisible by 2p plus 1, which is smaller, okay, if p is bigger than 3. So the proof is quite simple. Give a name, call it m for some reason, for 2 to the p minus 1, and let's let q be 2p plus 1. And therefore, if you plug in the formula 4m plus 3 for p, you see q has to be 7 mod 8. But by quadratic reciprocity, any prime that's 7 mod 8 has 2 as a quadratic residue. And so by Euler's congruence from the theory of quadratic residues, 2 to the q minus 1 over 2 has to be 1 mod q, and 2 is a square mod q. But q minus 1 over 2 is p. So 2 to the p minus 1, 2 to the p has to be 1 mod q. And so that tells us that q is a factor of 2 to the p minus 1. So 2p plus 1 is a factor. And this is consistent with the examples that we saw before. 11 is a prime for which 2 times 11 plus 1 is 23 is prime, and 11 is 3 mod 4, and 23 is a prime for which 2 times 23 plus 1 is 47 is also prime, and 23 is 3 mod 4. And so these are both primes, 11 and 23, which fit the hypotheses of Euler's theorem. And we saw before that 2 to the 11 minus 1 is divisible by 23, and 2 to the 23 minus 1 is divisible by 47. So Euler's theorem explains those factorizations, and if you believe that there should be infinitely many primes p that are 3 mod 4, for which 2p plus 1 is also prime, then Euler's theorem would tell us that there should be infinitely many Mersenne composites. So what's the deal with these prime pairs p and 2p plus 1? So these are not... Oh, question. Yes?
So in the previous heuristic formula...
Yes?
Yeah. So will it give a better approach if we replace n with just primes and we sum over primes instead of summing over all?
If you sum over the primes up to x, fair point, then how would things change? The sum of 1 over p up to x would be log x. So then the Lenstra-Pomerance-Wagstaff conjecture would turn into, if you replace the summing over all integers up to x with the primes up to x using our extra knowledge that n has to be a prime, the number of primes up to x that should make 2 to the p minus 1 prime, the model would suggest log x essentially. And their model, their refinement would you still have to multiply by e to the gamma. It doesn't recover the e to the gamma. Okay? But that's a fair question, right? As you know more, you refine your model. Okay? So you still need other heuristic reasoning to explain. You often have to adjust by constant scaling factors in this kind of a business. Okay? So Euler has this theorem which suggests there should be infinitely many Mersenne composites. It's a very weak theorem because we think 2 to the p minus 1 should nearly always be a composite, but at least it gives us conditions when we should expect a composite value. But what about these hypotheses that p and 2p plus 1 are both prime and p is 3 mod 4? Should that really happen infinitely often? And there are conjectures to take care of that. You don't always just make a conjecture, right? But there is a general principle about when we should expect several algebraic formulas to be prime at the same time. So we know that if p is 4m plus 3, 2p plus 1, of course 8m plus 7. Individually, there are infinitely primes that are 3 mod 4, and there are infinitely primes that are 7 mod 8. 7 mod 8 implies 3 mod 4. But in any case, separately, these expressions should each be prime infinitely often. What we need for Euler's theorem is for them to be prime at the same time, for the same m. This is still unsolved. Nobody has ever proved two linear expressions, even if they're individually known to take prime values infinitely often, that they're prime simultaneously infinitely often. And this falls under the label of what's often called Dixon's conjecture. So there's Dirichlet's theorem that a linear expression, an plus b, is prime infinitely often if a and b are relatively prime. But if you put together two linear expressions, an plus b and cn plus d, nobody's ever proved, if they're different expressions, that they're prime simultaneously infinitely often, even if we know that they're prime individually infinitely often. But anyway, Dixon made a conjecture about when this should happen, and this pair, 4n plus 3 and 8n plus 7, falls under the conditions for Dixon's conjecture. So we definitely expect that the hypotheses in Euler's theorem should work, that there should be an infinite number of those examples, but everything is still conditional because we don't yet actually know that there are infinitely many such pairs. So how do you actually verify that a potential number, Mersenne number with a prime exponent is in fact prime? How do all these things in the news, when they announce these numbers, how do they actually verify it? They're not doing trial division up to the square root of the number. It's just way too big. So they use what's called a Lucas-Lehmer test. So this goes back to Edward Lucas and Derek Lehmer, who, as the photos might suggest, were not collaborators. I think Lucas died before Lehmer was born. Go to Wikipedia. Lucas kind of died under strange circumstances. But in any case, so Lucas developed a test that could verify that Mersenne numbers were prime, and Lehmer strengthened the test so we have a nice if and only if condition. And so it involves a recursive sequence. So you start with the number 4, and you generate new numbers by squaring the previous number and subtracting 2. So I've written out the list there, 4, 14, 194, and so on. So these numbers get big pretty quickly, but we use them in modular arithmetic, so things stay under control. And the theorem is that if p is an odd prime, that the Mersenne number, 2 to the p minus 1, is prime if and only if the p minus 1th number in this list is 0 mod p. Okay, so it goes both ways. And so Lucas used some earlier version of this to determine the primality of 2 to the 67 minus 1 and 2 to the 127 minus 1. But Lehmer put the test in this form, and he had some electronic computational tools to apply it to discover new Mersenne numbers, Mersenne primes, or composites. So this is the Mersenne primality test that's actually used, the Lucas-Lehmer test. It's actually kind of tricky to prove why this works. You can read about it, but it's fairly tricky elementary calculations. So there's the Lucas-Lehmer test again. So let's see how this works in some examples. So we'll take two examples, 2 to the 11 minus 1, that's 2047. And so what we do is we take this recursive sequence, start with 2, square and subtract 2, square and subtract 2, over and over again. And so I make the list here. I'm going to start with 194, just because I can't start at the beginning and have it fit on the slide. But we do our calculations modulo the number of interest, modulo 2047. Take 194, you square it, subtract 2, reduce mod 2047. You get 788. Square that, subtract 2, and you go over and over, square, subtract 2, square, subtract 2. All your calculations mod 2047. And when you hit the 10th number, you don't get 0 mod 2047. And so the Lucas-Lehmer test said, it is not a prime. And of course we know it factors, with 23 as one of its factors. The Lucas-Lehmer test, though, does not give you a factor. It just says the qualitative statement, prime or not prime. So when it returns the answer composite, it doesn't tell you a factor. That's fine. If you're searching for Mersenne primes, you just toss it away and keep on going. So if we look at 2 to the 13 minus 1, then again, I have to start the table at the 5th number in the sequence because I can't get them all to fit on the slide. But each number, you square it and subtract 2, reducing mod 8191 every time. And when you get to the 12th number, you get the value 0. And so the Lucas-Lehmer test says this number, 8191, is a prime. Okay, so this is how the Lucas-Lehmer test works. You go up to the p minus 1th number in the sequence, mod mp, to decide if mp is a prime. Okay, any questions? Okay. So I wrote to the founder of the great internet Mersenne prime search to find, I guess I first read their website to find out how they did their search, and then I wrote to him with a question about it. So if you read the website, the way the great internet Mersenne prime search actually determines candidates for prime values of 2 to the n minus 1, of course it only sends out prime exponents for computers around the world to try out. So actually, it doesn't apply the Lucas-Lehmer test right away, because as we know, 2 to the n minus 1 is almost always going to be composite. So if we can get the compositeness early, we just discard it. We should focus the Luca-Lamer test only on the numbers that have a chance of really being prime. So first, you do trial division. This is the way the search works. You do trial division up to some bound to discover small factors. Once you find them, you discard and move on to the next number. If you don't find a small factor by explicit trial division, there's another algorithm you can use called the P-1 test. So tomorrow's plenary talk by Jeremy Teitelbaum about factoring with elliptic curves, he's going to discuss this P-1 test. So use the P-1 test. It's another more sophisticated way to try to find explicit factors. So it's a factoring algorithm rather than just simply a primality test. And then, if the first two steps don't reveal the number as composite, then this program that you can download onto your laptop to participate in this search will actually apply the Luca-Lamer test to the number. And it will determinately answer if it's prime or not. So there are probabilistic primality tests, which if you apply them to a number and it says the answer is that it's composite, is absolutely correct, assuming there's no hardware error. And if you iterate the test multiple times, you reduce, in some heuristic sense, the chance that it would claim a number is prime when it really isn't. And so I wrote to the guy in charge of this search. I said, why don't you apply a probabilistic primality test like the Miller-Rabin test before you spend your time on the Luca-Lamer test? And so he wrote back and said, actually, it wasn't like, oh, what a great idea, thank you. I mean, they were already thinking about that. Computational complexity of these probabilistic primality tests is about the same as the Luca-Lamer test. So they're waiting, and if the numbers get to have a couple more million digits, that he said they're probably going to start to include a probabilistic primality test as step 2.5 before they hit the Luca-Lamer test on the number. Okay, so anyway. So how does the Luca-Lamer test actually work? I'm not going to go through the proof here. It's kind of involved. But I want to point out that the special role of this number 2 and this weird process of squaring and subtracting 2, the numbers that are being produced have an explicit formula in terms of powers of 2 plus or minus the square root of 3. And what's special about 2 plus the square root of 3, or 2 minus the square root of 3, is that their coefficients, 2 and 1, fit the equation x squared minus 3y squared is 1. You could think about them as units in the ring z bracket the square root of 3. If you multiply numbers that fit this equation, this Pell equation, you get new numbers that fit this equation. And you're somehow repeatedly squaring over and over in this group. And you use this kind of group of numbers to explain where the primality test comes from. And so based on this idea, Benedict Gross in 2005 thought of an alternate Mersenne prime test involving not repeated squaring in the group of solutions to the Pell equation, but repeated doubling of a specific point on a specific elliptic curve. So there's y squared is x cubed minus 12x, and the point at the tip top of the oval there is minus 2, 4, and Gross suggested a way of using repeated doubling of this point, not necessarily with the rational coordinates, but with modular arithmetic coordinates, as a way of developing a test that's analogous to the Luca-Lamer test, but using the group of points on an elliptic curve in place of the multiplicative group of points on this, you might call it a hyperbola, x squared minus 3y squared equals 1. So by thinking more conceptually about what's going on at the Luca-Lamer test, Gross was led to find this alternate test. I'm not aware that it's actually been used in this specific setting, but people have kind of taken up Gross's idea and tried to apply it to other families of numbers in some way using elliptic curves, and hopefully we'll hear something more tomorrow about how you can use elliptic curves to actually factor numbers and not just decide if they're prime or not. So besides numbers of the form 2 to the n minus 1, computational number theorists, recreational number theorists have been interested in multiples of 2 to the n minus 1, where k is odd, k times 2 to the n minus 1. And so you can develop analogous criteria for when numbers of this form are prime. So Riesel extended the Luca-Lamer test, so we get the Luca-Lamer-Riesel test, and it actually looks the same, except there's a catch. The primality no longer implies n is prime. So there's the example. 7 times 2 to the 45 minus 1 is a prime, 45 is not. So in any case, so now we actually have to search through all exponents unless we're going to find some simple criteria analogous to the primality of the exponent for the case of Mersenne primes. And so we get a very similar test. If you take the same exact recursion, you get the same exact conclusion. The primality is the same for this number as the n minus 1th term in the sequence being divisible by the number, and it's the same recursion, it's just the initial value, S1, might no longer be 4. So the rule is if the k, the multiplier factor out front, is not divisible by 3, well, you can use for the first term in your sequence 2 plus root 3 to the k plus 2 minus root 3 to the k. It's an integer. The irrationalities cancel out. So, for instance, when k is 1, you start with the number 4 and use this squaring and subtract 2 recursion. But if k is 5 or 7, you have other initial terms in this recursion. If the multiplying factor is a multiple of 3, then the initial term is more complicated to describe. Okay? In fact, it might even depend on the number n sometimes. In any case, but the idea of the Lucas-Lehmer test can be applied to other classes of numbers that look similar to the structure of Mersenne numbers. Now, if you change the minus sign to a plus sign, the situation changes dramatically. Okay? Change 2 to the n minus 1 to 2 to the n plus 1, and you discover instead of infinitely many primes, we expect only finitely many primes. This is something that Alvaro had mentioned in his first lecture. Right? The Fermat primes, 2 to the n plus 1, in fact, now to be prime, n has to be power of 2. Right? No longer the condition is to be an odd prime. It should be a power of 2. But even then, we've only found 5 examples of n as a positive integer. 2 to the n plus 1 is prime, only known in the cases of 1, 2, 4, 8, and 16. Euler famously factored 2 to the 32 plus 1. Fermat claimed these were all prime, but 2 to the 32 plus 1 was beyond his computational ability to determine whether it factored or not, but Euler found factorization of it, and computers took over eventually. We've now found no more prime values 2 to the n plus 1. So this one appears to be prime only finitely many times. And if you allow odd multiplying factors, k times 2 to the n plus 1, there are some k's for which the expression is never prime. Forget Fermat's 5 prime examples. There could be no prime examples. So a famous example in this case is if you take k to be 78,557, that Sierpinski, I believe, showed that this sequence, when k is that value, is always composite. Those numbers are always divisible by that list of factors I've written down in the middle of the slide. So sometimes this expression is never prime. And so there's another massive collaborative computer search to see if 78,557 is the smallest example of an odd k that makes its corresponding sequence always composite. So this is called, I think, the Sierpinski number project, or maybe it was called 17 or bust, because at the time that they started doing it, they would like to check that every odd k below that number has a prime value of k times 2 to the n plus 1, so that 78,557 example is the first time this phenomenon of no prime values occurs, but the search that was being done, at some point the server crashed and they lost all the data. And so then they had to start over again. So then they moved the project over to this prime grid, and so it kind of took over. And now 17 or bust has become 5 or bust. There are 5 more examples of numbers below 78,557 for which no prime value of k times 2 to the n plus 1 has been found yet. And so the computers keep looking. So every time you just find one prime value, you can knock it off the list. So hopefully in our lifetime, we'll eliminate all of these and see if, in fact, 78,557 is the first time this all-composite sequence phenomenon actually occurs. Okay? So that's it for what I wanted to say. Thank you very much.